Welcome to today's webinar. The topic today is the verification of standardized steel joints using FE analysis in RFEM6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, the German and English webinars, new features, newsletters, and so on. I will be the moderator today, and I will also be the presenter. And my two colleagues will support me, but they can introduce themselves. Walter, it's your turn.
Okay, I had to turn on my microphone. Hi, my name is Walter Fröhlich. At Dlubal, I'm responsible for customer support by email and by phone. Furthermore, I'm a member in our development team for the add-on steel joints. Today, I will answer to your questions during the webinar.
Yes, and my name is Christian Wolf. I'm part of the product engineering team for the add-on steel joints, and I will also answer your question, so don't hesitate to ask if something is unclear.
Okay, thank you for your introduction. Then we can switch off our webcams so that the attendees can see the full screen. For the attendees who participate the first time, you can show or hide the control panel with that arrow here and then enter your question here, and my two colleagues will answer you. If you don't get an answer during the webinar because there are too many, at the end of the webinar, usually we get a lot of questions and we can't answer them during the webinar, then you will get an email afterwards. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's all for the organization. That's the content today. I will model and design DSTV connections in the steel joints add-on. And I will compare the results. I compare the load bearing capacity of the steel connections with the limit values of the DSTV guideline. The DSTV guideline contains the standardized connections. And I will say some words. Why should you use the steel joints add-on? What are the advantages? Okay, that's all for the introduction and the agenda. I start with our old program, RFEM5, because there are implemented the DSTV connections and all the values. Because of legal reasons, I can't show you the guideline in that webinar here, but I can show you the program. We have got, maybe I'll turn it off again, a simple model and a moment here, and we would like to define the connection here. And where are the DSTV connections? Rigid connection here. I had only one load, design internal forces, and this is the geometry. I will enter those or some of these values in our steel joints add-on. Those are from the guideline. So, and that's the design summary. I applied the maximum load of 141.5 kilonewton meter, and I got a design ratio of 100%. And I would like to design that connection in RFEM6, and we compare the results. In the first step, only the moment. In the second step, I will combine M and V, and the shear force as well. Okay, I can also show the connection in the preview. That's the preview. So then I turn to RFEM6, the same model. I had to do some preparations. We can't design a load case in RFEM6 anymore. We have to define a design situation. I can show it. And the first step, or that's the load case, design internal forces. And there's only one load combination with that load case and the design situation. And there is steel joints activated for. And of course, it's necessary to activate the steel joints add-on before. Here left above in the base data and under add-ons, it's necessary to do this check here. Okay, yeah, then I start with the types for steel joints. That order is activated if you or will be activated when you activate the steel joints add-on. So, and with double click, I can open the dialog here. I have to assign a node, that node here. Okay. It detects 3 members, and under members, I have to support at least one end. That's automatically defined. I can change it, but that it's quite good to have the support here on member 1. But member 1 and member 3 are continuous. That's the column, and the column is continuous. Okay, I don't change any base data here for the material or the section. Oh, I leave that as it is. Okay, then we have to enter the components. There are 2 possibilities. I can insert a component from the component database, or a complete connection from the library. I will show you 2 or both possibilities. So I start with a single component, an end plate. Now you can see here the different modifications: stiffening elements, plate, stiffener, haunch, end plate, fin plate, cleat, and so on. Okay, I choose the end plate. The connected member should be member 2. Here you can see in the window on the right side that it's selected with yellow lines. Maybe I can zoom a little bit in that you can see the changes. The reference member or members are automatically detected. So the material of the connection should be the same as for the members. The thickness of the plate is 20 millimeters. I choose here dimensions and position, and those are the values from the DSTV guideline. 390 vertical offset, and you can see the changes parallel in the window. So the diameter of the bolts should be 20. Bolt M20. And the strength grade for such a connection, for such a rigid connection, is 10.9. Okay, this is already good, but we need 3 spacings here, and we can increase the window a little bit. Okay, and now I have to enter 3 of the 4 values, and the last value is automatically calculated. So 30 space 100 space 180. Enter. Okay. So the shear plane shouldn't be in the thread, but in the shank. Okay, yeah, and at the end we have to define the welds. 7 millimeters for the flanges and 6 millimeters for the web. Okay, let me compare the values. That looks good. Okay, we can do a plausibility check. No error found. That's quite okay. And we can start the calculation. So at the bottom I have the button and I can start the calculation. Some of you could maybe already notice that I haven't the same moment as in RFM5. I can show you RFM5 again. The maximum value from the DSTV guideline was 141.5, and I applied a different value. And, let me explain that why I did that. I can't apply the same moment and then compare the design ratios, because we have got a non-linear material model, a plastic model, and that's why I can't easily compare the design ratios with for the same load. I will explain that on simple stress strain diagram. At first, let me wait for the results, or maybe I can already show the PowerPoint that we haven't, or we don't have to wait. Okay, that's the material model for the surfaces and solids. Yeah, for example, for the end plate and the flanges, the isotropic and plastic material model. So, and the maximum plastic strain according to the Eurocode is 5%. And we compare the plastic strain with the limit plastic strain from the Eurocode, the 5%. And imagine we get the result, we get plastic strain of 2.5%. Then we have got a design ratio for the plate of 50%. Yeah. So we would be in the middle, and then you can't increase the load. Yeah, you can multiply that by 2. Yeah, we would be here, and that's why I didn't apply the same load as in the DSTV guideline and compared the design ratio. I hope it is clear. But when you have got or when you get design ratio of 0% for the plate, then you are in the elastic area of the stress strain diagram for the end plate, for example. Yeah, it's a little bit tricky, but we can only compare the plastic strain. Yeah, we are, when you have a design ratio over 0, then you are in that area here. Okay, let's later I will try that with an example. Maybe then it's clearer. Okay, I turn back to RFM6 and I get the design ratio of 100% for the weld. And for example, when you double click on that line here, you get the design ratio for the plate, 34% or 45, about 45%, because the maximum plastic strain is 17% per mil. and the maximum plastic train is 50 promille or 5%. And we compare those two values. So, okay, let's turn back in the dialog. That's the, those are the formulas and the design for the welds. And if you want to get the submodel in the background, we create, or the program creates a submodel with surfaces and bolts or wheels for the bolts and so on. I will show you that model, and I would like to show you where you can find it. You can click on that button, left above here, and then you can see the design ratios. You can, for example, switch off some parts and so on. And left here at the bottom, you can press that button, and the submodel, the calculation model, is saved. So let's turn to that model. I open it. So, and yeah, that's the calculation model. Maybe I switch off the results and I show the different materials. That's the material for the plate, and the flanges and webs and so on. And you can see it's an isotropic plastic material model. If I double click on it, I can see that diagram that I already showed in the PowerPoint. Okay, and now you have got spokes for the bolts and shank, and those are the welds, the weld model. You can see the plastic material model for that surface here, and such rigid links. Okay, that's our calculation model. So then I turn back to the PowerPoint. Our first connection, I showed you the values in RFM5, the maximum DSTV value 141.5, and I applied 151.5 in the steel joints add-ons. It was a lot of time to prepare those connections. I had to try until I reached the design ratio of 100%. And when I compare both moments, I get a ratio of 1.07. The maximum moment in steel joints is 7% higher than the DSTV guideline, but only when I apply the moment only. I have also combined M and V, the moment and the shear force. The maximum shear force according to the DSTV guideline is 321.9, and I applied 98% of the maximum values, and I got a ratio of 98%. In that case, we are lower with the maximum load. I can show you the model. So that's the same model, and maybe I can switch on the transparent model. I applied shear force here and the moment, and both are 89% of the maximum values according to the DSTV guideline. And I got a design ratio of 100%. All connections that I show you today can you download on our website. At the end of the webinar, I will show you where you can find the models. Okay, then we turn to the next steel joint, next connection. Also a simple model, a main beam and a secondary beam. We have got one load and we get a shear force. I can show the shear force. Is it? Oh, it's not calculated yet. The shear force should be the half of 125 kilonewton. Internal forces we set with values. Okay, yeah, 62.5. Okay, so I turn to the steel joints. To assign the node. Okay. Yeah, one member should be supported, that's okay, and the main beam should be continuous. So, and this time I don't use, I could use the components. Here you can see the cleats. I would like to assign a cleat. This time I use the component library with all the predefined connections. So then you can see the general categories, the rigid connections, beam to beam, beam to column, with haunch, column stiffness, and so on. Then the pinned connections, cleats, thin plate, and so on. Then the trusses, welded trusses. Well, we already have got a lot of connections implemented. Then the bracings, and we will extend that library continuously. I turn back to the pinned connections, beam to beam, and I would like to define a cleat or two cleats on both sides. That's why I have to apply the template, and we have to wait a short moment, and then we can see in the preview the two cleats. Okay. We leave the library and we have got to do some modifications. So, okay, I zoom a little bit in. Okay, member 2 is the member that needs to be connected. That's the main beam 1 and 3. So the offset is 10 millimeters, that's okay. Material is okay, S235, but the section needs to be modified. I select an equal leg angle. The width is 100, thickness 10, then 12, radius and 6. That's okay. So the position should be, it's clear on both sides. I can only also assign only one cleat. In my eyes, that makes no sense. Both. Then definition type, I like the length and position to enter the values. Length is 150 millimeters, no eccentricity. So okay, then the bolts. M20, but this time M20, and the strength grade this time 4.6. So I have to enter only one value. The other values are calculated automatically. The same for this 30. Okay. Shear plane and thread, no. Then for the other side, also M20 and 4.6 as strength grade. Then 40 and 40 and 55. And shear plane not in thread, but in the shank. So, okay. Then the plausibility check, no errors found. Okay, I can calculate the connection. So, and in the meantime, we open the PowerPoint again. That we skip the calculation time. That's the pin connection. The principal beam is an IPE 360 and the secondary beam IPE 200. The maximum shear force according to the DSTV guideline is 62.58, and I applied the same load in steel joints and got a design ratio of 100%, means that we can apply the same load as in the DSTV guideline in that case here. Okay, let's turn back to FM6. It takes some seconds. In combination with the GoToWebinar software, it takes a little bit longer than without, but we have to wait. And the design ratio is 100%, about 100% for the fasteners that time. You can double click on it, or you can also use that button here, design check details, and you also reach the dialog. And that's the design check ratio for the bolts. And you can see all the equations from the Eurocode here. Okay, that's all for that connection. We turn to the next prepared model. Now, the same model you can see in higher load, and we would like to, or I would like to apply another connection with a thin end plate. So that's why I open again here the steel joints dialog. The same node number 3. Oh, it didn't get it. Okay, now members, one supported end, and the main beam is continuous. So the components, I use an end plate. The connected member is again member 2. Same material as for the members. The thickness, a thin plate, 10 millimeters according to DSTV guideline. Dimensions and positions, 160 150 minus 25. Oh, no. Minus 25, 0, no eccentricity. So then the diameter of the bolts are M20. Didn't get it. Okay, M20, 4.6 is okay. The values are okay, but not the number of bolts. So, and then 40 space 70. Okay. No shear plane and thread. And if you zoom in, you can click on the welds. You can see there's no weld for the flange. We can deactivate it. But for the web, you can see it's selected, and we leave the 3 millimeters. Okay, then let me do a final check. Oh, that's okay. So then plausibility check, no errors found, and we can run the calculation. So we turn back to the PowerPoint. That's the next connection. The same beams, IPE 360 and then the IPE 200. The maximum value in the DSTV guideline is 114 for the shear force, and I could apply a load of 141. The shear force is quite higher. Maybe the DSTV guideline is quite conservative for such connections, and I got a ratio of 1.24. Okay, let's turn back to the program. It's already calculated. This time the weld has the maximum value. Okay, then to the next connection or the next prepared model, almost the same model, but I applied an eccentricity for the beam here, for the secondary beam. That means that we have to cut the member. Just imagine there are a grillage or a sheet on the top of the beams. That's why I defined such an eccentricity. So, okay, and we have considered that in the connection. So I open steer joints again. Have to define or select the node. Then the same procedure here. So, and now I don't define connection. I already defined the connection before the webinar and saved it in the library. And now I would like to load that connection from the library. That's what you can do for your connections as well. It's a pinned connection. A pinned connection. And now you can see the beam-to-beam templates here. And you can go only the predefined or only the user-defined connections. There's only one connection or all. So, and I select it and apply the template. And the template contains the cleat and the member cut. We can see that in the preview here. Okay, so we leave the dialog and load the connection. Now you can see the cleat and the member cut. So we do a plausibility check. No errors are found. So, and we run the calculation. So we turn back to the PowerPoint. Yeah, that's the pinned connections with the cleat or the cleats, and the IK is the cut. Yeah. And in the DSTV guideline is the maximum value 43.42, and I could apply only a load of 40.5 in the steer joints add-on. Yeah, that's why we get a ratio of 93%. Yeah, our load that we can apply is a little bit smaller than according to the DSTV guideline. So we turn back to the program, and you can see the maximum value is for the plate about 100%. You can double click on it, and you can see the maximum plastic strain is about 5%. So, and now we can try that. We can decrease the load. Yeah, for example, I can apply only 80% of the load on the connection. I can enter a formula here. 81 multiplied by 0.8. Okay, and the program calculates the value automatically. So now we have got only 80% for the load, and if we run the calculation, we don't get a design ratio of 80% for the plate because of the nonlinear stress strain, the diagram, the nonlinear material behavior. Yeah. So maybe in the meantime, I can go back in the PowerPoint. Let's show the diagram again. Yeah, we had a design ratio of 5%, and if I apply 80% of the load, I don't get a design ratio of 80%. It's much lower. You will see that. It's 43% now. Okay, then we turn to the last connection for today. IPE to IPE 400. And I would like to apply a rigid connection here with end plates. So types for steer joints, steer joint. I have to assign the node here in the middle. Okay. Members are supported, or one member is supported. And I load also a component from the library. I had, before the webinar, I prepared such a connection, pinned connections, and you can see here the defined connection. And I apply the template. Okay, so if I press OK, it overtakes the predefined and saved connection. You can do a plausibility check. That's okay. Okay, and then we run the last calculation. So let's skip the calculation time. We turn back to the PowerPoint. So that's the last connection. Beam IPE 400. The maximum value according to the DSTV guideline is 213.1, and I could only apply 189 kilonewton meters in the steel joints add-on in RFM6. Yeah, we can apply only a load of 89% of the maximum load from the DSTV guideline. And it will be a little bit decreased if I also apply shear force. Let's show you the results. Okay, you can see 100% for the fasteners. Okay. Yeah, that was the last connection. You could see we have got different ratios, different results for one connection, the same ratio for both DSTV and the steel joints. Yeah, there are two different approaches. The DSTV guideline calculates the maximum values or maximum ratios with the component method, and steel joints uses the finite element analysis. Two different approaches and similar results, but not the same. I think that's clear. But maybe you ask, why should I use the steel joints add-on when I sometimes can apply only a smaller load than in the DSTV guideline, for example, or other guidelines with standardized connections. Yeah, when you calculate structure in FM6, for example, and other programs, you usually do that in the 3D model. Then you get internal forces, also MZ or torsion and so on, and then you can't apply the DSTV or other standardized connections, for example. And if you have got only, for example, for this connection, only a moment and the shear force, just use the DSTV guideline. But when you have got in 3D structure and you get, for example, torsion or MZ or normal force or shear force in direction of the weak axis, then you can't use such standardized connections. At least, for example, for this connection, when the normal force isn't, I think, higher than 10% of the plastic normal force. And with the program steel joints, that you can consider all those three-dimensional internal forces. And that's, in my opinion, the best feature for this add-on, the main advantage. Further advantage is you don't have to import the internal forces from external programs. You usually calculate a more complex model than I in this webinar. Then you pick the nodes and you create the connection and you calculate the connection. You don't have to import any internal forces. And these internal forces are, and moments and so on, are always up to date. When you change the structure or increase or decrease the loading and so on, you only have to run the calculation again, and the steel joints add-on uses the current internal forces. The next advantage is there's no black box calculation. I showed you the detailed FE model, and you can check and analyze that if you want. Also, the connections are visualized in a very high quality. And you have got the results of the steel joints add-on in the same printout report as for FM6. Okay. Yeah, I hope it was quite interesting to you. For me, it was interesting. I was curious. What will be the results when I compare the DSTV connections with our steel joints add-on? You could see, similar results. Sometimes a little bit higher, sometimes a little bit lower. But in the praxis, you usually have got three-dimensional internal forces, and then it's necessary to use the add-on steel joints when you use RFM6. Okay. If you want to get a free product demonstration or non-binding offer, now just contact our sales team. You can click on that link here, or you can scan the QR code. I will show you where you can find the PowerPoint slides. Also the recording, we record our webinars. That's why I turn to our website. Just a moment. So, dlubal.com, and then under news and events, you can find the webinars. This is today's webinar. Next week, I will present the most frequently asked questions of the last month. And at the end of the month, 29th June, I will present the new features in the steel joints add-on. Okay, that's today's webinar. I click on it. In the next days, you will get an email with a link to that page here. Then you will find the recording here in the middle, and you can already find the presentation slides here and the used models here. And you can download the models, of course. Okay, that should be all. Maybe a last hint or last wish when you leave the webinar. It would be very nice when you take 1 minute to answer some questions. You can score the webinar. Just note that the worst score is 1 and the best score is 5, as you give stars. You can enter wishes for future webinars. But if you don't have any wish, you can enter a sign minus also. That would be very nice when you take the time. I thank you for your attention. Thanks to Walter and Christian for answering your questions. I wish all a nice rest of the day. Maybe we meet each other in a future webinar. Bye-bye.